Hello everyone. In this video, we're going to review another method of addressing the heteroscedasticity issue. This is called the method of weighted least squares. So how do we deal with heteroscedasticity issue? The first method that we have reviewed is that we could just construct heteroscedasticity robust standard errors and test statistics after WLS. And that's very convenient because we don't need to know the exact form of heteroscedasticity. So that's one solution. Now there's another solution that exists, and that's what we're going to learn about as the weighted least squares approach. Now this is the case where we have some knowledge or where there is some way to come up to express this exact nature of heteroscedasticity. So if we are able to specify the form of heteroscedasticity, then in that case, we can use the weighted least squares method. And if we're able to correctly specify the nature of heteroscedasticity, then the efficiency from the WLS or the weighted least squares method is actually greater than the traditional OLS method. So if WLS estimators are more efficient, then it means the variance of our beta hats from WLS models are actually smaller than the variance of our beta hats from the OLS regression. So if our specification is correct, things work out in our favor. But if our specification of the general form of heteroscedasticity is incorrect, then that's a problem that we'll have to deal with. In which case, one of the solutions is to do WLS and then construct heteroscedasticity robust test statistics there. So all that I've said so far may just sound a little vague right now. So let's go ahead and understand what WLS is all about. So first, we'll focus on the very simple case where we can express heteroscedasticity, the exact form of that, and we actually know the general nature up to a multiplicative constant. What do I mean by this? Well, whenever there is heteroscedasticity, variance of ui given xi is sigma square I, right? It is no longer a constant, but varies with the x's. Now, suppose we are able to pin down how this variation happens using some functional form of x, okay? So I'm now going to rewrite my variance of the errors as sigma squared multiplied by some function h of x. Sigma squared is a constant, h of x is some function of x. So now I've been able to rewrite my variance as a functional form of x. As x varies, my variance will also vary. Now we're going to assume that we know what this functional form is. We know what this h of x actually is. We have an expression for that. And we'll see an example in just a moment. But another thing to remember is that the variance is generally positive. Variance of anything is positive. So we know that sigma squared is a positive number. So for variance of u of x to be positive, u given x to be positive, this h of x, this term should also be always positive. So we'll keep that in mind and let's go ahead and learn how WLS works out. Now, for a random sample that we take from the population, sigma square I is just your variance of the error term. And we're rewriting that as sigma square times h of xi. For simplicity, instead of h of xi, let's just call it h sub I. Now, let's take the simple example of a savings function, where savings is now dependent on income of the person. Now, this error term here in the simple linear regression, we're going to assume that there is heteroscedasticity in the model. So the variance of the error given my x values, given my income, is now no longer a constant, but rather a function of the x variables. And I'm going to assume in this simple case that this h of x function or the h of income function is just given by the actual income variable. So therefore, my variance of ui given income is now sigma square times h of x. In this case, it will become sigma square times income. So I've now been able to express my heteroscedasticity using a very particular specific functional form, which tells me the relationship between the error variables and the x variables. Now, let's go ahead and look at the standard MLR model. Okay. So this particular example is just given as a motivation to illustrate that we know the functional form for heteroscedasticity. We know the general form for heteroscedasticity. Now let's go back to our MLR model. We have yi as a function of kx variables. Now we have heteroscedasticity in this model. Now what we're going to do is we're going to transform this regression model. How specifically are we going to transform this? We're going to divide every variable throughout on the left and the right hand side of the equation by square root of hi. Okay, and the reason for the square root will become clear in just a second, so bear with me. So the transformed variable is now y over square root of hi, and every single term on the right hand side is also divided throughout by square root of hi. Now, in other words, I now have a transformed variable where all my y and x variables, I'm denoting them with an asterisk, y star, x star, and so on, where every x star is just the original x value, x variable, divided by square root of hi. Now, let's go ahead and focus specifically on the variance of this transformed error term. Now, variance of ui star is nothing but the variance of ui divided by square root of hi. Now, the variance of this is just the expectation of the square of this term. And where is that coming from? Variance of ui given xi is just expectation of ui square given xi minus expectation of ui given xi, the whole square. Now, if MLR assumption 4 holds, this second term will just be 0. So your variance is just expectation of ui square. So applying a similar logic here, variance of ui given root of hi is just expectation of that term, the whole square. So it is just expectation of ui square divided by hi. And we know that expectation of ui square is nothing but sigma square times hi, because we have assumed that that's the variance, right? So we have assumed that variance of ui given xi is sigma square times hi. We know this functional form, and that's what you're seeing here. So sigma square times hi divided by hi boils down to a constant. So what's just happened? We've taken our original model, and once we know the form of heteroscedasticity, we have transformed our original model such that the error term in the transformed model now has constant error variance. So once you've transformed the model, the heteroscedastic error has now vanished and you're left with a homoscedastic setup. So if we were to use this in the savings example, where savings is just a function of income, our hi was just given by income sub I. So if I were to divide every term by the square root of hi, I'll be dividing every term on the left and right hand sides by the square root of income sub I. And that will be my transformed model. And this transformed model will have homoscedastic error terms. Now, though we're getting around this problem by running a transformed model, the coefficients that you so get from the transformed model should be interpreted with the original model in mind. What do I mean by that? Beta naught and beta 1, I'm getting the coefficients from the transformed model, but beta 1 in the original model was actually giving me what? The marginal propensity to save. That same interpretation will hold in this case as well. Beta 1 is still interpreted as the marginal propensity to save. And you should always remember that all the coefficients have to be interpreted in light of the original model. So what has WLS helped us do? It's just allowed us to transform the models now such that the error terms have constant variance. And this is called your weighted least squares method. And you're essentially, what you're doing is you're weighting your errors by some particular function, which helps you get homoscedastic errors in the end. So WLS is nothing but you're trying to minimize the sum of squared errors in the transformed model. So weighted least squares is nothing but when you run this transformed regression model, any OLS regression involves trying to minimize the sum of squared error terms. So if I'm trying to minimize the sum of UI star square, I'm just trying to minimize the sum of squared errors in this transformed model where there is a weight attached, or I'm multiplying every single variable by some factor. This factor is what I call the weight. So the weight here is you're dividing throughout by square root of hi, right? So when you actually work out the math, you're trying to minimize the sum of squared deviations where you have this hi term going up in the denominator. So if we write variance of ui given xi to be sigma square times hi, the larger the variance, so the larger the h value, the larger the variance will be. So if there is a particular term for which the variance is really large, then if I just weight that large variance, that large deviation, square deviation by this hi, the denominator is also going to be a large number. So intuitively, observations that have a large variance will also have a large denominator with them. Therefore, they tend to, the actual importance of such observations will tend to become smaller. So this is what we mean by saying that observations with larger variance will get a smaller weight when you're trying to minimize the sum of squared deviations. So this is essentially what the method of WLS is all about. Once you know the general form of heteroscedasticity, you define that, and the form is just sigma square times hi. Once you know hi, all you have to do is get a transformed model where you divide the left and right hand sides by square root of hi, and you just run that model using OLS. And that is what your WLS is all about. Now, WLS in theory, by theory, is supposed to give you variances which are smaller than the variances that you'll get from OLS. So we'll see in an example in just a second how that works out. And WLS is therefore more efficient than OLS. Weighted least squares are a function of something called the generalized least squares. And in fact, OLS models, as we know them, are just a very specific class of the weighted least squares, where the weight attached to every observation is just a constant. The weight doesn't vary based on the variance of the error term in the OLS model. So this is what WLS is all about. So here's an example where the net financial wealth of single individuals is regressed on a bunch of explanatory variables. So if you look at the first two columns, the dependent variable, net financial wealth, is regressed just on the income of the person. So I think if their income goes up by $1, their net wealth goes up by 82 cents in this case. If we use the weighted least squares model, for an extra $1 of income, their net wealth goes up by about 79 cents. But notice the standard errors here. So the OLS standard errors are a little bit larger than the weighted least square standard errors. So this is in line with our statement that WLS models are more efficient than OLS. And that's why they have smaller standard errors. So the same pattern continues to hold, a similar pattern continues to hold when you add in more regressors as well. So if we add in the other regressors, notice that the coefficients are changing a little bit between the OLS and WLS, but the WLS standard errors are a bit smaller than the OLS standard errors, telling us that WS is more efficient. Now, the coefficients are a little bit different between OLS and WLS. If they are substantially different from one another, then we should worry about model misspecification. But that is not something that we'll probe in this example further at this moment. So this concludes our discussion of weighted least squares. And in the next video, I'll do a follow-up to this where, here we're assuming that we know the general form of heteroscedasticity, right? And it's a very arbitrary thing to do. And we may not always know this general form of, we may not always be able to find what this hi is. So we look at a very special case of regressions where just the way in which we run the model leads us to find what the weights are. So we'll look at that, and then we'll see the more general cases in a subsequent video. So I'll see you there.